Okay, so the recording has started. Uh, let's. I'm sharing my screen. Just tell me if you like if my screen gets unshared. Okay. Uh, I'll be sharing this screen basically. Okay. I hope you can see my screen, right? Can anyone give me a confirmation?
Yes, it's visible.
Yes. Okay. Thank you. So hello everyone. Welcome to the reinforcement learning course. This is the first session, so it will be more of an introductory session, and I'll share you the course logistics and how you'll be communicating throughout the course. Okay, so it can be like I'll ask you what you are comfortable with. So let's start the course, and then we'll discuss how you can share the resources. Okay, so I hope my screen is visible. So yeah. So yeah, this is week one of reinforcement learning course, and this URL that you can see is actually the Python course that I took last time. So I would really recommend you to go and check out the Python course there. So why I'm saying this, because reinforcement learning is mostly a theoretical course here, right? But what I want to do is also show you some hands-on on how to code these systems so that you will be more confident about the theory. So just learning the theory and memorizing it would not always help, rather than if you know how these systems are implemented in code, right? Then it will be more beneficial for you in, let's say, you are in research or you are in any academic or industry role. Implementing these systems actually is really helpful. So if you are new to Python or need a refresher, then just go and check out that course, or you can like refer to any other material that you have for Python. Okay. Now, a short introduction about me. I'm a PMRF research fellow at IIT Kharagpur, and these are all my like like if you can check out the videos I have for like the works that I am doing in IIT Kharagpur. All like demo videos are there, and you can check out our lab UBNet. These are the URLs for the like uh, for the YouTube channel as well as the LinkedIn page. So now I work in like ubiquitous computing and sensor networks. So what does it mean, and where does ML come in this entire thing? Like ML RL comes, right? So ubiquitous systems are those systems which blend in our day-to-day life, help achieving some crucial objective of our own, let's say reminding us of something, or tracking our behavior, or these type of things hugely improve our life, but they mostly remain out of our attention span. So we don't really put a lot of attention to those systems, but they improve our life like significantly. Okay. So that systems are called ubiquitous systems. For example, your Wi-Fi, right? Your Wi-Fi can have multiple use cases like tracking what you are doing, or let's say understanding when someone. So Wi-Fi has been largely used in scenarios when we want to detect fall. So when an elderly person tip off in the floor, this Wi-Fi system can actually produce alerts to other members of the house that okay, your grandfather or grandmother had tippled off in the floor, right? So those are ubiquitous systems. Um, or nowadays you have also seen these Aura rings or smartwatches, all those things, right? Those also comes under ubiquitous systems. Now, these systems, because they are interacting directly with humans, need a way to adjust their behavior based on human preference, right? In that case, RL gives us really good tools to kind of like harness these signals from human, harness these preference signals from human, Oh, I think my screen content sharing has been off, right? Yes. Sorry, I don't know what is happening, but for some time my screen gets unshared quite a few times. Just let me know whenever it gets unshared. Okay. So like to make this system adapt with our preferences, we need reinforcement learning. Okay. So you can go check out my profile if you want. And this is the YouTube channel. So all the videos will be in there only. Okay, so you can, if you need a refresher, you can go to the YouTube channel so you can get a refresher of the course. Yes, and these are some of the systems. So I just want to briefly touch them. One is a sensor node can be deployed across a house to understand when activities are happening. So, for example, when someone is cooking, or when someone is going out, or when, let's say, they have left the oven on and left the house, all those high stake scenarios can be identified and alerted to the human, right? Uh, and we did a lot of data collection in this front across India. And also we are trying to understand how outdoor is impacting indoor. So like, let's say there is a huge garbage dump near my house, right? And how it is impacting my household's air. For example, if I have a preconditioned person who has asthma or something, is how I can account for them. So how I can uh, like brace for harmful pollutants. If I know that they impact my indoor in such ways, how I can brace for them. Okay. Some other uh, things that we are trying to do is also like activity recognition, or what someone is cooking. So if I know, let's say someone cooks a particular food item daily, right? Then he will be deficient of some macronutrients or micronutrients, and I can recommend that person to have these micronutrients, or change their kind of eating habits so that they remain healthy for a long time. And also, these are some other works that I'm doing, is like how to make these air pollutants visible to us. So these are not visible, right? So we can make them visible with augmented reality and extended reality methods. Okay. So if you want, you can go check out our like these demo systems in our YouTube or in the lab page. Now enough about me. So and these are some of our collaborators and stuff. Okay. Now enough about me. Let's talk about the course logistics. So like you are listening to these video materials that are there in the NPTEL site, right? Apart from that, what we will do, we'll also try to code these systems, and for coding these systems, we'll use standard Python. So I recommend using this Anaconda Navigator or Miniconda Navigator. So what advantage does it give? It comes with all the packages. You can download anything of your preference. Okay. So I personally prefer this Miniconda and Anaconda Navigator, and we will be using this Jupyter Notebook IDs to, why? Because it gives us a really cool way to debug our code. Okay. So we can quickly debug our code instead of doing like print statements. We can check intermediate outputs in different cells. So that would be really helpful for us. Okay. So assuming that you already have something in your system, if you don't, you can install it. Okay, we'll move forward. And these are the Python resources that you want to, if you want, you can go look into it. Now, for the course material, this is the course material, overall course material. Okay. So week one will be mostly about introductory stuff. So the setting of RL, what are the different learning paradigms we have in AI, and all those things. Okay. Now, second week will be around bandits algorithm. So let's say you have multiple levers to pull. You can only pull one lever at a time, right? And basically you can pull only one, and then your term end. Okay. So by replaying the game multiple times, how you can figure out which one is the best lever. This is what called bandits algorithm. Okay. Uh, okay. And then there are some proofs about, okay, what can be the best and good, like best or the lowest like gains that you can get with a bandit algorithm. And finally, we have reinforcement learning, MDPs, all those stuff, Bellman equation, like this dynamic programming approaches, eligibility traces. Oh, wait. I guess you can see my screen again, right? Yeah, and finally, after eligibility traces, we have function approximators. So as function approximators, we can think of it as a neural network. Okay, so neural networks are known as universal function approximators, and so we'll see that so there are actually two type of RL that I will discuss. One is classical RL and one is deep reinforcement. Okay, so until eligibility traces, there will be classical RL. Okay, beyond classical RL, there will be this function, like use of this general function approximators as neural networks. And there are many methods like DQN, DDQN, policy gradient. All those advanced methods use this function approximator or a neural network to learn the policy or how to behave in an environment. Okay. And finally, we'll close up the entire course by hierarchical RL. And an example of a hierarchical RL is your AlphaGo. Okay. Uh, can you turn, Abhishek? Wait. Yes. Uh, okay, so like just unmute yourself whenever you want to ask a question. Otherwise, just stay muted. Okay. Okay, so this is our entire uh, course layout. Okay. So as you say, hierarchical RL is example. One of the good examples are AlphaGo. Okay. So the Go playing agent or the chess playing agent, those are hierarchical RL agents. Okay. Now today's agenda will be to learn about the entire AI space, how it is factored into different learning algorithms or learning paradigms, and then the general RL setting. What do we mean by RL scenario? Okay, or where we can apply reinforcement learning, and then we'll try to understand. Like there is a term called world in RL. Okay, so you are the you are interacting in a world to get a signal about how to behave optimally in that world. Okay. So that world can be modeled in different flavors. So we'll see how this world can be modeled. Okay. It's, you can think of world as a toy gaming example. Okay. Oh, yeah. Okay. So yes. So and we'll try to code this world. Okay. We'll try to code these worlds. And finally, we'll discuss about the evaluation criteria and how we can communicate over the entire course duration. It can be through WhatsApp, or it can be through Teams also. I prefer WhatsApp. If you can create a WhatsApp group, I can append it to the slide so that everybody can join. Okay, and there you guys can discuss about the doubts over the week. Okay, so okay, just create a WhatsApp group and send me the QR so that I can append it in the slide at the last page. Okay. Okay, so this is the AI space today. Okay, so there are a lot of learning paradigms, and uh, so I like like bigger bubble is called AI or artificial intelligence, and then within it there are many algorithms. Okay, there are this heuristic algorithm also, for example, A star or pruning algorithms, all those things. Okay, um, so beyond this algorithm, there is a paradigm called these are called a classical AI. Okay, and then within that there is a special category of algorithms which are called machine learning. So what it does when machine learning comes into picture is you have some data, right, and you want to learn about the data. That's where machine learning comes in. Okay, so all the other algorithms which don't directly require data but is some kind of an AI algorithm. For example, A star. A star is a pathfinding algorithm. Okay, or for example, a crude example can be Dijkstra. Okay, it's also a heuristic based pathfinding algorithm. Those are early examples of AI algorithms. Okay, pathfinding algorithms, flow algorithms, all those things can come under an umbrella of AI. Okay, we are getting some intelligence from a computer. Okay, in some way, in a heuristic or in an algorithmic fashion. However, when there is a huge data comes into the picture. Okay, there is a data, right? There is a data about some phenomenon, not some particular thing of some phenomenon. Let's say some phenomena like uh, a function from body weight to diabetes, let's say, right? So there is a huge table where you have body weight and diabetes in the two columns. So you want to learn how body weight is related to diabetes, right? That this data, whenever this data comes into picture or any kind of data comes into picture, that falls within this machine learning circle. Now, within machine learning, there are different learning algorithms. So in all these cases, all these small bubbles, right? Data is common. There is some data. Okay. So there are algorithms. Yes, yes, you can get the PDF. So I'll share you all the resources, no worries. Uh, so this is a group called supervised learning. There is a group called, oh, sorry, my screen gets unshared for some reason all the time. Okay, I think now it's visible again. There is a circle called supervised learning. There is a circle called unsupervised learning, federated learning, and reinforcement learning. And all of them kind of have a common circle called deep learning. So basically deep learning intersects with all these learning paradigms. Okay, so what does it tell us is all these learning paradigms have some kind of statistical models as well as this general purpose neural network in it. Okay, so apart from statistical models, there are general purpose neural network models which are common across all these learning paradigms. Okay, and whenever this neural network comes, that's a separate field called deep learning. So yes, so this is the deep learning circle. Okay, it intersects with all these things, and whenever it intersects with reinforcement learning, there is this deep reinforcement learning group. This DQN, DDQN, policy gradient, all those algorithms are deep reinforcement learning. Okay, and this remaining part is called classical reinforcement learning. Okay, so you'll see. Okay, so let me create a WhatsApp group. I'll share it in the chat. Wait. Give me some time. I'll create. Let's just finish some part and then see. Now, now let's see about these algorithms of where they comes into picture. The supervised learning, right? Supervised learning is we have some data, labeled. So, for example, the weight to diabetes or images of cats and dog, and they're labeled. Which one is cat, which one is dog, right? All those things are. Wait, let me. Okay, which one is cat and which one is dog? All those things are um, part of like supervised reinforcement. So we train the model or we supervise the model on labeled data. Okay, so for example, in the image, you can see it's trying to detect different shapes like triangle, like rectangle, square, pentagons, all those things. So we have those labels and their shapes. A model or a model means a mathematical model. Okay, a mathematical model learns uh, how to classify these images to different shapes, like shape categories, and that's the supervised learning task, like supervised learning uh, example. Okay, so for example, a example could be how many glasses of water is required to cook how much rice. So how much water you should put to cook how much rice. That's a that's a supervised learning task that you can learn. If you have some data, like if you collect some data from your neighbor or anybody who cooks daily, right? And then you train on, like, see that data multiple times, you'll learn how to, like, how much glasses of water I should put in the rice. Okay, that's a part of a supervised learning task. Then unsupervised learning. So what is it? Oh, okay, good. So you have created the WhatsApp group. Wait, let me do one thing. In the chat, it's the WhatsApp group, right? Let me add this over here. Okay, and then I'll share it over here also, and in the the sheet that you all also have, right? Um, I'll share that one there too. Okay. So there is a common sheet also, okay, where you can find out all the videos, all the slides. So I'll share this one there too. Okay. So yes. So what is unsupervised learning is, you have some similar some data, right? Let's say this different colored dots, right? And you want to cluster them based on their type. Okay, so red balls will be clustered at closer to each other, blue balls will be clustered closer to each other, and green balls will be clustered closer to each other. So a good example can be how we sort different fruits. So let's say you are tasked to, oh, sorry, yes. So you are tasked to sort different food items. Um, and you can just see them and then sort it out, right? Which one is, let's say, apple, which one is banana, or which one is kiwi. You can sort it out based on just looking into it, right? And even if somebody don't know the name of the fruit, they can look into the fruit and, okay, these are similar, so group them in a similar group. Okay, so that is called unsupervised learning. Okay. Okay, and finally, this, like, our uh, like what we are trying to learn, this reinforcement learning, right? So reinforcement learning is when there is some word, okay, let's say a maze, okay, and there is some agent, let's say a mouse, okay. The mouse wants to, let's say, find food in the maze, okay. Let's say maze is a jungle, okay. Now the mouse wants to find food in the maze. Uh, okay, any other example of unsupervised learning, right? Uh, any other example of unsupervised? There are so many, right? I cannot think of one, but anything. So let's say you find a new butterfly, right? New cat type of butterfly. Yes, making friends in social media, right? That's also a kind of unsupervised learning. So you look into them, right? Look into their profile, try to match with the match, or try to identify, okay, these looks like my type of people. I clustered with them, right? You basically make friends with them. So that's also a type of unsupervised learning. You don't really know whether they're good or bad, but by just seeing their profile, analyzing, you try to group them, right? So this looks like not my type of people. This looks like my type of people. So I'll send them a friend request. Okay.
So,
So
but
that's
then this,
also,
yeah, but then this grouping is also a kind of clustering only. So I'm looking
yeah.
for an example of the unsupervised wherein the kind of the grouping or the clustering is not there. So what about this Gen AI stuff
Ah,
wherein I give
yes,
something
yes.
and then get something out of it?
Got
Would
it.
it be an
Got it.
example of unsupervised one?
Yes, yes, I got your point. So another unsupervised learning is how to reproduce your data. So let's say I have some missing data. Okay. So let's say I have an image of an actor or somebody. Okay, I have an image of a person where due to some reason some part of the image is corrupted. Okay, so the so there is another group of those are called self-supervised learned model. Okay, not unsupervised as such. These are called self-supervised learned model. So basically what it does, it learns to reproduce the data without that missing part. Okay, now like self-supervised and unsupervised, they're actually very close. Okay, why it comes between the supervised and unsupervised based on how much missing data you provide. If you provide like entirely noise, right, and try to produce something new, right, that's kind of a unsupervised model. But if you put some incomplete data and still able to learn some representation, that's also called, that's like more closer to, like less closer to supervised learning, but it is in the middle ground. So those are called self-supervised learning. So for example, these Gen AI models, right? So Gen AI models initially they are self-supervised, or they try to reproduce data from a huge database. So let's say a huge data corpus, right? Uh, so the model try to fill up. So for example, how ChatGPT is trained, right? It is trained to fill up missing sentences, right? Missing, let's say there is a poem, and then let's say 50% of the poem is striked out, or kind of like omitted. Okay, and the model learns to how to reproduce those missing parts. Okay, yes, there are lots of examples. So just to a crude example is clustering, but this supervised, self-supervised, and unsupervised, there is a huge kind of application of these models in Gen AI. So mostly things are self-supervised, or basically you learn from data, try to reproduce missing data, and in some cases it's unsupervised also. Okay, yeah, well, anyway, just if you have any doubts, just let me know. If you want me to go more into detail about how unsupervised methods are applied, then just tell me. Okay. So did I answer your question?
Yeah, fine,
Yeah.
thanks. Yeah.
Okay. Okay. So yes. So now the reinforcement learning part, right? So we assume there is a world. We'll see how these worlds can be modeled. Okay. My screen gets reshared for some reason. I don't know why. Maybe I have not restarted my computer for a long time. That's why. Okay. Now mm, there is an agent who tries to behave optimally in the world, and there is some reward component that they are getting. So for example, the mouse can find food in the maze, right? The objective of the mouse is to, let's say, get away from the maze, right? Or get out of the maze, or it can be roam as much as possible in the maze, right? Or it can be just maintain his health and roam in the maze, right? Based on his objective, the reward function changes. So if the mouse desperately wants to get out of the maze, then the reward can be negative of time, right? So as long as he spend in the maze, he'll get more and more penalty, right? Now, if the mouse has an objective of roaming the maze, then positive of time, right? So it tries to maximize the number of, like, the time he or she spends in the maze. Okay. Now, if the mouse has another objective of, let's say, being fit and just roam around the maze, maintain his health, then the objective is to not only stay in the maze for longer period of time, but also try to find food, right? So this reward function, or this reward, gives us a motive in a world. Okay, for us, let's say, as humans, right, we are also, our reward function mostly changes over time. So when we are kids, right, our reward function is to play as much as possible, or for nowadays, see phone as much as possible, right? Or for whenever we are in, let's say, teenage ages, right, teenagers, then our objective is like, for example, our objective is like perform good in class. Okay, and also try out different stuffs. Now, in like beyond 20 years, or when you are trying to settle up in society, right? Then our objective is to, okay, now we have to settle up. So our reward function changes based on in what age we are in, right? So based on that, so our entire world changes basically. Okay, so these stages, these teenage years, this adult period, these all these things have different reward functions as well. Okay, so so instance that will basically discuss multiple times is this mouse and grid example. Okay, so when the mouse can have different motives, so we'll stick to one motive, is to find food as quickly as possible. It might not leave the maze, right? uh, might not, like, leaving the maze might not be a good option. Maybe that's the world, that's the earth for him, right? So he cannot kind of have a objective function to leave earth. Okay, until and unless it has a uh, as a, like, imminent threat or some uh, threat that can destroy everybody, right? So unless and until that is happening, we are not leaving earth. So for the mouse, this maze world is his world. Maze is his world. Okay, now his objective is to stick there, find food as quick as possible. So uh, basically he wants to maintain his health. Okay, and what it observes, so what it observes around him. Okay, around, like, everything that is around him, and the actions that he can take, that the mouse can take, is left, right, up, down. So we can see the maze as a like from a top projection. Yes, no worries. So we will see the maze, or will observe the maze as a top projection. So the mouse can only take left, right, up, down. Okay. So those are the actions that the mouse can take for our model world. Okay. So the mouse has some kind of a representation of the world, right? That is called its internal state. So these are the kind of terminologies we have. There is a reward function. There is this environment or world. The mouse or the agent sees some kind of an observation, builds its internal state, and based on the internal state, it takes some action in the world. And the objective is defined by the reward function it has. So this might be very clear, right? Where is the learning in the, yes, learning is, it cannot take random actions, right? So behaving randomly would not take the mouse anywhere. So the mouse would learn how to find the food quickly for us, or how to be healthy within the maze. So it would be able to find the cheese. See, there is a cheese here, right? So it will be able to find a way to reach to the cheese. That's where the learning comes. So behaving randomly would not take the mouse anywhere, rather than a more informed approach of where I should go, like how to learn that informed approach or the policy. Okay, sometimes this sequence of optimal actions are known as policy. Sequence of actions, not optimal. There can be suboptimal policies too, right? Where the mouse can detour a longer route and reach to the food. Or what you can do, can, okay, go on a shorter way, right? That's a more optimal policy. So learning this policy of the or the sequence of good action is our objective in an RL setup.
And
Is it
who decides rewards in this setup? The
yes,
one who is designing the RL algorithm or what?
yes, the one who is designing the RL, not necessarily the one who is designing the environment.
Okay.
So sometimes what happens is, let's say for this course, right, we'll be designing our own what this environments. So we have to put in this reward function for us. So like what type of behavior we want, we'll put in the reward function based on it. Okay. Now in most scenarios, when we try to implement this RL algorithm in real world, there is a system, right? There is an underlying system. Let's say I want to make quad a quadruped walk, right? Then there is a world. There is a physical world we want to behave optimally in. In that case, we have to somehow model the reward function. There is an underlying reward function that if it doesn't behave well, it will topple off, right? But accessing that reward function is sometimes very hard. We cannot access that reward function as our own. So then as developers, we need to also model a proxy of the world that, oh, wait. Okay. So sometimes the reward function is given to you, or sometimes you have to design reward function. Like for example, for us, right? For us, reward function is given by society. Okay. So people will tell when someone is performing good or performing bad. They might have an internal reward system that, okay, I know that I am performing good, right? But most of the time, the real reward comes from the world, not from an internal representation. Okay. So for a for a quarter fall, let's say, right? Whenever it fall down, it will get a -1. That's a valid reward function. But from that reward function, that's the original reward function that you are getting from the world. But that's a very sparse signal. So you cannot learn very quickly from that signal. So as developers, what we have to do, we have to build in very like a very dense reward signal, how its motor should function, how its joints should function, uh, like a proxy rewards function that can help it learn more efficiently in the world. Okay, so there is a world reward function, but we sometimes modify the reward function for easy learning. Okay, okay, and the entire RL suite of algorithms, right? They learn how to behave optimally in the world. So observing the world and taking some action in the world and getting the reward. That is the loop. So the mouse observes some world, it takes some action, it gets a reward. Okay, so again, it observes the world, takes some action, gets some reward. By interacting with the world, it tries to learn which action is best, not in a single time step, rather than in a kind of in a forward view. Like it tries to identify which action would be best in, let's say, next 100 steps. So observing how the system, how the world is, it tries to estimate, okay, if I do this, then in possibly next 10 steps, I will reach to the food, something like this. There is this notion of far sight, like foresightness. So I can, the agent might be able to plan ahead in the environment, as we do, right? As we always do. We don't take action just by looking our current situation. We think through our actions. Slide is not visible. Oh, sorry. Yes. I hope it is visible now. Okay. So this think through thing that, okay, I will plan in future, that is also there in reinforcement. Okay. And this is the like formal setup of reinforcement. So these notations you will see a lot of time. So ST is the state. Okay. So there is an agent called agent, let's say agent, right? And then it takes some action AT to the environment. The environment gives him two things, a reward RT+1, and T is time step. So you can think RL setup as a discrete time step environment. So the world moves in time steps, T+1, T+2, T+3, T+4, like this. Okay. And within that T step, the agent decides something. Okay. So if the T-1, this delta T is very slow, then it's a real time system. So it is very slow. It is less than our perception. This we have perception around 100 millisecond. Okay, so if the system timestamp, this delta t is less than 100 millisecond, for us it's a real time system. Okay, okay. So but yeah, the degree of real time can be more shorter. So it can be like a microsecond response time of the world also. Okay, so the agent takes some action, environment reacts with next state and reward. Okay, and this reward goes into the agent again. And where it takes the action from, it takes the action from the previous state, so ST, and the previous reward RT. Okay, it doesn't always take into consideration the RT. RT is just to learn the uh, good policy, but mostly by seeing ST, it tries to formulate an action. Okay, act on the environment and see, okay, what is the next step, what is the next reward.
But then where is the objective function here, and how this the appropriate value of the reward is going to be learned?
Yes. So we are not learning reward. Reward is part of environment. So
Oh, I see.
the agent is decoupled from the environment. Agent is the RL algorithm. Okay, it tries to learn how to behave optimally in the environment. Environment gives us reward and state given I provide it action. So for let's say for the entire course, you will assume that reward function is something that is part of the environment. It will not change, and uh, let's say a environment decides how a agent should optimally behave in that. My still okay. Okay. So let's say reward can be finding food, right? Then that finding food reward will be given to the agent. Okay. So like for example, I can show you a quick thing. GitHub. So we'll use this library a lot. I have this library I coded earlier. Yes, so this is a library. Yeah, I think you can see my screen, right? So you can actually design this type of grid worlds, the custom grid worlds, just by using this type of a character pattern. Okay, so if you just write a character pattern, it will give you a graphics for that world. Okay, and you can interact with the world with this method. Wait, yes, these methods environment.step action. So if you step into the environment with an action, it will give you next state reward, whether you like whether the environment has ended or the agent has died in that environment, and in some kind of your info means your warning variables and stuff. Okay, so this is a library we'll be using. Okay, so with this library you can create this type of worlds. Okay, and in the code, if you see, let's say this is the world. Okay, now how the reward is placed, all these states, it's -1, reward is -1. Okay, and the object these are holes. Okay, O are holes, and this G is the goal state. So we have a very high reward +100 in the goal state. That's the reward function for the whole system. Okay,
So
and yes.
sorry to interrupt you. Yeah. So can we model this RL problem as a supervised problem, supervised learning setup, wherein the goal is to maximize the reward points. Goal is to maximize
Yes,
the reward, and
yes.
then I mean rest everything will get identified.
Yes, got it. So that's a really good question. So we can also, because we have the reward function as a supervision, right? Some kind of a supervision. We can also model it as a supervised problem. But the thing is, you see, uh, the genetic supervised algorithms are not aware of time. They are one-step solutions. So from some observation, you just giving a one-step solution, right? It doesn't have any notion of time or future steps. So how the action would lead in future. This notion is not there in supervised learning. So reinforcement learning is that thing. So given this short-term rewards, there is a single step reward. Wherever you land, there is a reward there. Wherever you next land, there is a reward there. But the objective is to kind of give us a policy or a set of actions that leads to the goal. So there is this notion of time, right? A time optimal action. So where I am and what would be the best action, right? Even if the reward is same, based on the time, the action might be different, right? So all these states has reward -1. But let's say I'm here, then my action should be right. If I am standing here, my action should be up. So this notion of capturing time is there,
Yes, I understood.
right?
Yeah, thanks.
Yes.
Yeah.
So that's why this reinforcement learning is actually uh, a supervised scenario only. But there are two different things are there. One is this notion of time, or based on where you are in the environment, the action might change irrespective of the reward signal. And another thing, this reward signal is very low information. So the reward signal is not very dense in information. Okay, it just gives you right or wrong information rather than how you should go in there. So it doesn't say how. Okay, it doesn't say how, it just say good or bad. So supervised learning needs this how thing. Okay, so you can go and check out the code also. So for example, read world here, read world.py, right? Reward, reward. See, this is the reward function. So see, all the states are reward -1. The goal state, if the type is goal, then the reward is +100. If the type is a whole state, or where the agent, if the agent land in a whole state, it basically dies. Okay, then the reward is -100. And if other state, the normal states are -1. That's the entire reward function. Okay, so in the grid world, it will, yes, here it will look something like this. All these states will be -1. Only these whole states will be -100, and the goal state will be, oh, sorry, my screen has unshared again. Yes, and the goal state will be +100. And it comes bundled with the environment. So we'll just design algorithms to exploit that reward. Okay, and learn how to, like, what is the shortest route to reach the goal. Okay, okay, and these are the different terminologies that we have. State, RT, and the symbols will be reused everywhere. Okay. Now, like today, we'll see how this world is modeled. Okay. Algorithms comes later. First, we need to understand how the world works, right? So we'd be able, like, world can be of anything that the agent can interact in. So it can be real video games, right? The games we play, there are also, let's say, on average in one game there are 18 to 60 actions that you can perform. Okay, and 60 different actions that you can perform at a single time. Um, and you basically are exposed to the graphics of the game, right? So let's say I'm playing some kind of a NPC shooter game, right? So then I'm getting view of the different players and where I am in and all those things. That's the state for me. Okay, and whatever I can do, let's say fire or a duck, or let's say hide somewhere. All these actions are uh, in my arsenal of taking these actions, right? Action sets, and the reward is whether I can stay alive in the game. Okay, how long I can stay alive. So my reward signal will be +1 for 1 second. So if I stay alive for the next 1 second, I will get a +1 reward. Okay. So now that obviously these games are real, like very good representation of worlds, right? But we may not be able to code a game in this course. So rather we'll use a simpler world. Okay. Yeah. So world is mostly modeled by this Markov thing, Markov worlds. Okay. So we'll first see what is the Markov assumption. Okay, so there are two assumptions. One is that you can predict the next state, or the next whatever will happen next from the current state. You don't need the history. So that means if you know all the history of the world, right, you can obviously predict the next state. That's a, like a fact. So if you know everything about a system, then you can directly predict what will happen next, right? But this is very hard, or not tractable in real world. Okay, so what Markov does, it relaxes his property to be, like, we can predict a environment but by just seeing the last, like just observing the last state of the environment, I can say, okay, what will happen in the next. Okay, that is called Markov property. So basically it's a memoryless process. It doesn't have any memory. It don't need any memory to predict what happens next. It just sees the last state, it predicts, then or it moves to the next state. Not predicts, it will be a better word to use, moves. So a Markov system will move to the next state based on the current state. It doesn't care about the entire history of the system. Okay. And another thing is, let's say it moves from state A to state B. So that probability of moving from state A to state B doesn't change over time. So it's a stationary thing. Okay. So there are some systems, let's say four-dimensional systems, right? Not necessarily four-dimensional systems. Those are called unstationary systems. Okay. So where these are all four-dimensional systems, if you can think. So if a state of you can think of a Markov um system as a gas. Okay. A gas moves in an atmosphere. So it starts with some initial state and then it, let's say, spreads across time, right? So from which state to which state it transition is kind of a continuous, yeah, that's the continuous analog of a Markov process. So the time delta that is there for moving from one state to other state is very small. For example, how a gas can spread. That's a Markov chain. It spreads as a Markov chain. Okay. And stationary means this transition probabilities of state 1 to state 2 doesn't change over time. Whenever the gas again sees a state 1, it will move to state 2 with the same probability. Okay. And there can be multiple states it can move to. So state 1 can lead to with, let's say, 50% probability to state 2, with 30% probability to state 3, and with 10% probability to state 1 again. So this type of a, uh, yes. So it's like an NFA. Okay. With some probability, it can move to a particular other state, or it can loop back to the same state. So these two properties are very important. One is Markov property and this stationary assumption. Okay. So stationary assumption means the world is stationary, and Markov property means from the past state only I can predict the future. I don't need to know the entire history. Okay. And based on these two assumptions, there are many category of worlds. So one is this Markov process. So what does Markov process mean? So it's just a memoryless process. It doesn't give us anything. It doesn't take in anything. A good example can be, let's say, spreading of a gas. Okay. Or yes, so it doesn't give us any reward as such. It doesn't take in any reward, any action as well. It just moves to the next stage, next stage, next stage, right? It just spread across the space. So that's a kind of an example of a Markov process. You can give me another one if you can think of. Then reward process. So Markov reward process is whenever we have some reward out from the system. So Markov reward process. Can I think of any Markov reward process? I cannot say farming because farming needs action, right? Uh, so it's a process where you don't directly involve in taking action, but you get the reward. Okay. Or let's say something like this. Or let's say you can also think of Markov reward process. Someone is taking some action. I don't care who is taking the action, but I get the reward. That's a Markov reward process. Okay. Um, I cannot think of a really good real world example of it. Uh, it can be like watching a cricket game, right? We don't take any action. We just sit there in the couch and the game plays out. Somebody is taking some action that who is part of the, I am not part of their team, right? So I am as an agent, I am not interacting with anything. The environment is evolving. So the entire 20 overs or 50 overs is going on. I am just watching it, panning across different stages. And the reward I'm getting is I'm getting in, like I'm entertaining myself, right? So that's the reward. Yeah. So that's the Markov reward process. And Markov decision process. So I could not get the last question. Wait. chess game can be Markov, this chess game can be a Markov process, right? But if you are, it can be a Markov reward process if you are observing it from outside, not playing it, right? And it can be a Markov decision process when you are playing it. Yes, reward can be both negative, negative, positive, zero. It's a real number, any real number. Okay. Yes. So yeah. And finally, there is this Markov reward process. So what does it mean is you are also taking decision. So the agent, that's basically your grid world, right? Or any playing chess is also a Markov decision process where you are observing the world, you are taking some decision, you are interacting with the world and getting some reward. That's the Markov decision process. And there are other uh, kind of world models also which are POM-DP or non-Markovian. So non-Markovian means where this history is required. You cannot directly predict what is happening, what will happen next by just observing now, okay, or the current state. For example, our world is non-Markovian. Okay, Chinese chess game is it Chinese checkers game? Yes. So that Go, right? Go is Chinese checker game, I think. So Go is a Markovian process. So if you know the if you can see the board and if you know I will play, let's say horse, right? In that case, you know, okay, what will be the next step? It will not be something unknown, right? So whatever you can see the current state, you know the action, you can pan out, okay, what will happen next? That's the Markup process. Yes, it's just jumping over pieces. Markov reward process, what is the scope of that in our study? So Markov reward, these processes, right, that we are studying are actually world models. So the entire RL suite of algorithm runs on a world, right? So these are models of the world, and we need to know how these worlds work so that we can, and there are lot of terminologies that will reuse from the, for example, state transitions or what is a policy in a world, all those things we need to learn the RL algorithms. Okay. Reward process is important. So directly jumping to decision process, because RL comes when decision is involved, right? So Markov decision process is where the entire thing starts. But knowing reward process is important because I told you, right? So reward process is basically you are observing from outside, someone else is playing. So in imitation learning how to play by watching some other agents play, all those things are kind of using this notion of Markov reward process. Okay. So we'll see all those things are necessary. And this is an incremental thing. So we'll code Markov process, we'll add a single term, there will be a reward process, add another term, Markov decision process. Okay. Okay. And there are like intermediate theoretical concepts from Markov process to reward process, from reward process to decision process. Okay. Finally, this POM-DP means partially observable Markov decision process. Okay, and non-Markovian means that history is required. We cannot predict the future by just looking into the current state, which is our world. So you cannot predict what will happen tomorrow just by just seeing today. You have to know some history. Okay. Now this is a theoretical example of a Markov process. So you see there are three states C, S, and V, and the system can only transit between them. So for example, of chocolate, vanilla, and strawberry. So it can be uh, a mental model of how I choose ice cream. Okay. So if I have taken strawberry yesterday, I'll choose with 10% probability chocolate, with 40% probability strawberry again, and with 30% probability um, vanilla. Okay. So this is an example of a Markov process. Now, if these states have reward, right? So I like strawberry with some.
Excuse me, sir. Arrow mark, what does it represent? Direction of arrow?
Direction means the transition direction. So from vanilla to strawberry, the probability is 10%.
Okay. And vice versa, it is 30%.
Yes,
Strawberry
yes,
to vanilla, 30%.
yes. So you see, from a particular state, you can only transition with a probability total as one, right? With 30% go to chocolate, 30% go to vanilla, 40% you self loop to strawberry.
Means I am at say strawberry, yes.
Yes.
So that means whatever, what will be summing to one? Say
Yes.
in
So
yes.
from each state, the outward probability will be one only. Total outward probability will be one. And
Okay.
yes,
So point 0.3 plus point 0.3, to sum it up, they made it point 0.4 within itself,
yes,
just to make it one.
yes. Because from a state with 100% probability, you will go somewhere, right? So with 30%, you'll go to chocolate, with 30%, you'll go to vanilla, and with 40% probability, you'll just stick to strawberry.
Okay, that is why here stick to that is like a buffer variable.
Yes,
There
it's
they
like
have
a self
just
loop.
put,
Basically, goes back to the same, this self loop.
it will not
Okay.
transition.
Yes, not transition. It stay in the same state. So for
Say safe,
example, yes,
uh,
right?
okay, safe state.
Yes, self state. And for example, in chocolate also, you see, uh, the chocolate self loop is 70%. So if someone is in the chocolate state, he will self loop with a 70% probability. Okay. So from just seeing the system, we can say that the whoever mental model he is, this is right. The person loves vanilla most while modeling. Uh, while modeling a process as Markovian, how these probability values are yes. So we'll see that. So when we'll be coding these systems, right? We'll see how we can actually write up these probability values. Okay, so we will be coding this system, no worries. So two things are important. One is this set of states. See this, there are two things to define a Markov process. The set of states S and the transition probability PTR. Okay. So set of state, what are the set of states? C, S, and V, and transition probability PTR. That's a matrix of a square matrix of state to state transition. So the rows will be S like C, S, and V. The columns will be also C, S, and V, and it's a square matrix of transitions. So from C to V, what is the transition probability? That will be there in the cell of the matrix. Okay. So that's a example of a Markov process. Now
Okay, so diagonal will represent
self loops.
its own transition.
Yes. Uh, who decides these probability values in the time? That the world itself is the gives us the probability values. So like as developers, we can obviously design a world, right? And we can um, design these probability values for ourselves. But in most real world examples, the physical world gives us the probability represented, like probabilities. Okay. And sometimes these probabilities are actually not known. So there is another classification. What I am currently telling you is um, how these worlds are modeled. Okay. So later on we'll see, based on what I know about the world, there is another kind of classification of RL algorithms. So it's called model based, model free, and then deep reinforcement. This model based and model free comes under one category. Okay. So no, these are just how we can model the worlds. Okay, just assume that we know the yes. Can general RL problem be mapped as some sort of yes, yes. So RL in general, RL algorithms, not all RL algorithms, most of the RL algorithms works under the assumption of a Markovian world. Okay, okay. Some algorithms are there. For example, policy gradient. It doesn't care whether the world is Markovian or not. Okay, but this DQN, DDQN, all these things, they assume the world as a Markovian, then build up the algorithm. Okay, so there are two things, meaning they must be completely not deterministic. Deterministic means, see, Whenever there is a probability, the world is probabilistic. If the probability is 1, then it's a deterministic world, right? It's still a probabilistic world, not deterministic. Um, with 30% probability, it goes to S to V. So if you play 30 times, it's not guaranteed that you will get like 10 times. Or if you play 10 times, there is no guarantee that you will get 3 times to S to V, right? Even 50-50, but if you toss a coin 10 times, there is no guarantee that 5 times it will be head, 5 times it will be tail, right? It will be 50-50 if you toss it million times or 10 million times, still probabilistic, right? Still close to 50-50, not exactly 50-50. So it's still it's a known stochastic world. It's not deterministic, okay? And example of a non-Markovian process is, let me share my screen again. Yes, uh, slide is not visible. Yes, I see reshared it again. And a non-Markovian is ours, right? Real world is a non-Markovian process. So you cannot tell what I will do next by just seeing me now, right? You have to know a history. Like by just seeing me now, right? You cannot tell what I'll say next. You have to know, okay, I'm teaching reinforcement, so you will say something about reinforcement, right? But just observing me for 1 second, you can say what I will do in the next minute, right? So that's a good example of a non-Markovian world. You have to know some history.
So, sir,
Well,
that does it mean Bayesian and Markovian
yes,
Bayesian
Bayesian and Markovian is
are
so
opposite, right?
not opposite.
Not opposite.
Bayesian, Bayesian,
Bayesian, given something happened,
uh-huh,
what is the probability of occurring of this event? Given
yes,
that another event happened,
hmm. Yes,
you are
yes. So that,
asking,
yes, so it's actually not opposite. So
not
uh,
opposing.
yes, let me go back to the previous slide, this slide. See, it's still a Bayesian world, but the history has been relaxed to the previous state only. This is the Bayesian world, right? Where you know the history
Yes,
and you can
yes.
predict what will happen next. For a Markov Bayesian world, the history is reduced to last state only.
Uh,
Okay.
okay.
Okay. And this probability transition probabilities are static. So those are static means these probability transitions are already known. Okay, and then they don't change over time. So if you see a world, it will not directly change to 0.25 after seeing the world. It will be stationary across your observation. So all the time the S to V transition will be with 30% probability only.
Yeah, you have shown this in this graph.
Mhm.
So what do we make of this graph? What is the use of calculating these probabilities, transitioning probabilities?
Yes, yes. So we'll see how to model this world. So how to model our, like let's say you need to be able to design algorithms that learn from some game or some interaction method, right? For example, this thing, this we need to implement the algorithms, right? So how this thing is implemented, that background is needed. Otherwise, all the theoretical analysis we'll do right later, it will slightly go over your head. So until and unless you know how the world works, you cannot learn it. Okay, so
Okay,
this is a world where there is a simpler version of the world where there is only state transitions, there is no reward, there is no action. Okay,
okay, okay.
that's called a Markov process. Now when the reward comes, then basically you can transition with some probability that's there, and there is some reward, right? Then this is a Markov reward process, and these terms are actually important. The state S, transition probability PTR, it will be same across your entire theoretical analysis. Okay. Now there is this transition dynamics is there, so so the probabilities are not there, but you can assume some values, right? The main important thing is this reward components. So waking up has zero reward. Watching Netflix has some self loop, so you can binge watch some episodes, right? That's a -2 reward. So that means that's a not a, so from an initial perspective, it's not a good state. Okay. Code and debug. It's also very tiring, so it has some reward. Going to nap, so waking up and going to nap, there should be a probability here, but for this diagram it is not there. Some like waking up and then taking a nap has a really low probability. That's why that arrow is not there. Okay. Now from nap to wake up, there is a probability. Okay, taking a nap has a one reward, so it's a good thing. And from after coding sometime, it's going to sleep has a very good reward. So, and then after you debug the code, right, and deploy the code somewhere, it has a very high reward. So in this world, the motive is to deploy the code and rest, right? So you take rest, you debug as less as possible, watch Netflix as less as possible, and deploy your code. That's your world. Okay. And actions are not there. Okay, so this is just, let's say, it's the states that you mostly spend time in. Okay, actions are not there. Okay, and so the things are, there is a state, there is a state, number of states, a state set, and there is this probability ptr, a reward function r, which is a function of state, right? Which state you are in gives you the reward. And the gamma, gamma means, we'll say gamma. What is gamma? It's a discount factor, comes later in the theoretical part, but there is a gamma thing there. Okay, just no. Finally, this is a Markov decision process. So that means there is a state one, there is a state two, and an end state. Let's say three states only, with some x and x and some x and y you can take, and you can, these are the reward values, right? Okay. Yeah. Should there be a transition arrow from sleep to wake up, or the agent restarts everything? Let's see. From sleep to wake up, there should be a arrow. It's not there. Anyway, these are like toy examples. Okay. Maybe this is a daily routine thing, right? After you sleep, that's the end of the day. That can be that, right? But usually if it is a continuous process, there should be an arrow from sleep to wake up. Okay, anyway, this, like, from there it looks like the sleep is a terminal state, because you cannot go out of the sleep state, right? There is no um, like outward arrow. So basically it's a daily routine stop. After the day stops, the agent just sleeps and the entire learning algorithm just restarts again. Okay. Now in the descent process, you can see there is actions available again. Now you can take action X or action Y, and based on that, it will transition to different states, right? And you can see different rewards. So the, see this right side text, you can see previously it has only S and P. Now it has R and gamma. Finally, it has action. So SAR, SAP, R, gamma. So 5 tuples or 5 constructs to define a Markov decision process of a world. So that's our work. Let's code. So to do, like, let's try to uh, see how we can code these systems. Okay. Now here I should add two things. These are how you can define a reward process, right? Theoretical concept, return. Okay. This concept of GT, return, that will say. And for the decision process, we have another decision process. We have two theoretical uh, policy. Fine. So there are two theoretical things that we need to know. One is for the reward process, we need to know the return concept of a return. Okay. And finally, the decision process, we need to know the concept of a policy. So let's just code them. So it will be very clear to you. If I know the probabilities, I can code the system. Okay.
Sir, I just have one question. Can you hear me,
Yes.
sir?
Yes, I can hear it. Go ahead.
So if I see the slide number 18 and 19, right?
18 and
Almost
19. Yes.
as world-wise, they are the same.
Hmm?
They are looking very similar. There are states and then rewards. Here, there
Hmm?
also there are states and rewards.
Hmm?
Can I imagine like when I'm making something as a Markov's process, when I have to decide a reward function, then I have to undergo the process of Markov's reward process, and then when
Hmm.
I'm trying to design the policy, then I have to come to this background of Markov's decision process. Is it like
Yes.
that, or
Yes. Yes. So it's based on whether you are interacting with the system or not. If I am as an agent interacting with the system, then I need the Markov decision process. If I am not interacting, then and it's basically changing on its own or somebody else is interacting, I'm just observing. Then I don't see the action probabilities from my own, right? I just see how the model change, how the environment changes, and I just get the reward. So only thing that changes from reward process to decision process, now it's a more detailed environment. I can see the actions now also. I can take the actions now. So Markup process basically it's changing on its own. I don't see anything. Reward process, I see rewards only. Now this is, I also see the actions that I can take in the environment. This is basically more zoomed in look of the same environment.
okay? When I'm
Okay.
designing an environment, then I also have to provide rewards for a given state when
Yes.
I'm coding my environment.
Yes. So we'll code these environments only now. Okay. So you'll see how in code how these probabilities can be kind of represented. Okay. So first we'll code a markup process. Okay. So let's open up uh, mkdir npdl rl. Yes. Yeah, I hope you can see my screen. The markup process we have and the image I'll take from here. This is the process I want to code. Okay, so the transition probabilities and everything will be same. So if I just do a screenshot, say within documents. Yes, this is our model, right? Let's name it mp.png. So we can, so this is how you can also image src mp.png and sorry, yes, but we need to also provide width 100 pixel. Oh, it's very small. 300 pixel. This is our world. Okay, want to code this. So we need libraries like import. Only NumPy would be there. Okay, NumPy is only required. I don't think any other thing is required for now. NumPy. Okay, now what are the two things that are required there? So if I go back to the slides, state and transition probability. These two things we need to define. That's how we code the entire Markov process. So state S is what? 0, or let's write C, V, and S. These are the states, right? And now okay. Now transition probability, PTR. PTR is a matrix. P dot matrix of what? State to state transition. So yes, these are the values. Let's say, and this is basically CV, like chocolate, vanilla, strawberry. Like those are in the column as well as in the rows, right? So first one is chocolate to chocolate. What is the probability? 0.7. Then, and let's say the columns, I can write it here actually. The columns are chocolate, vanilla, strawberry. Okay, and the rows are also chocolate, vanilla, strawberry, right? Oh, we should have actually written, like, anyway, this is the matrix. Okay, so 0.7 for chocolate to chocolate, then chocolate to oh sorry, chocolate to chocolate, chocolate to vanilla, and then chocolate to strawberry. Chocolate to vanilla has a 0.2 and chocolate to strawberry has 0.1. So 0.2, 0.1. Then same thing for vanilla. Vanilla to chocolate has 0.1, vanilla has 0.8 and 0.1. Then this should be 0.1, 0.8, 0.1. And finally, for strawberry, right? Strawberry to chocolate has 0.3, strawberry to 0.4, 0.3. So that means 0.3, 0.3, 0.4. Okay, so this is our world. We can actually write things like this. This is chocolate, vanilla, strawberry. This is chocolate. Oh, sorry. Here we have to do chocolate, vanilla. Yes. So S and B, two things are there. We have already defined our Markov process. Now we need to define this transition probabilities, right? So how transition probability is done is, it will be better if I can connect my graphics pad with it. It's important. Because how these transitions happen is actually a very important thing. Okay, I have my graphics pad connected. Mm. We have a yes, this one. Okay. Okay. So these are what. Now we have this probability matrix, right? Now let's say the states are actually encoded into one-hot vectors. So
The screen is not.
screen. Okay. Yes. So yes, let's say C, V, and S, right? Based on which number state it is, we basically represent it as an one hot thing. So basically, it's like representing a classical state. So C means C has 1 probability, other two has 0 probability. Okay. Similarly, V means C has 0 probability. Being in C has 0 probability, being in V has 1 probability, and being in S has 0 probability. Similarly, S is like 0, 0, 1. These are like one hot representation of the states, right? So these are basically classical states. So a system can be in a state with 100% probability. And then we have state transition matrix, right? So if I just C VS CVS, say 1, 0, 0. If I multiply it, what is the slice I will get? This, again, this, and this is right. So we'll basically slice up this row. So if I just multiply 1, 0, 0 with the matrix, I'll basically slice up the first row, right? That means the probability of transitioning from C to my writing is bad because I have not installed the graphics drivers for the drivers for the notepad. Like from C to C. Uh, Nobody's not responding. Wait, some technical issue. Yes. Okay. So this row actually means the probability from C to all other state transitions, right? So it can transition to C, it can transition to V, or it can transition to S. So by just multiplying its classical representation with the matrix, we slice up that row. Now, if I just do, let's say this is 0.7, this is 0.2, and this is 0.1, right? Now I can just sample from these states. You can just do sampling, right? If you do sample, you will with 70% probability you will go to C. With 20% probability you will go to V, and with 10% probability to go to S. So this is basically sample, or in Python, we have a function called random choice that sample for us from a probability distribution, right? So that one will do. So two things we need to code now. One is how to convert the state to its classical representation, or basically their probabilistic representation. and how to sample. So two functions. State to, so let's have a mapping of state to probability vector. Okay, or let's say not name it state to probability vector, state to classical. You can think of it as a classical state, right? Where a object or anything can be there with certain probability. So S C has a, because it's the first state, has probability of 1 0 0, right? And let's write it as an NP array. Next, V array 0 1 0 and S share my screen again. 0 0 1, right? Now I need to, this is my state to transition. Now let's say I am at C. Okay, start state is equal to C. I marked it as C. Now what will be my transition code? First we need to get the classical state representation, right? So state to classical, we passed it C, or the start state, right? It gives me that classical representation of the state, and then we just multiply np dot multiply, or not multiply, macmul matrix multiplication with the PTR, probability transition dynamics, right? So what it gives us is actually the row, actually this row of transitioning to other state from C, right? If I am starting at V, C, it will give me the second row, this row, right? And if I am transitioning from S, it gives me the state transitions from S. Okay. Now, for example, we start from C. Now, this is my transition probability dynamics from state to this. Now, we need to sample. So, this is the probability of transitioning to other states. Now, the sampling code is like this: np dot random dot choice. And in choice, what we need to do is we need to provide, oh, sorry, random dot sample, not choice. Yes, see, this is choice is the right one. So A is the list of choices. Z is the size. Size, we want only one transition, right? We don't want multiple transition from there. We can only transition to the next state. So size will be none or one. We'll say none. Okay. Replace equal to true. So we'll take one. So replace equal to true doesn't make any impact. Okay. And P is the probability transition. So this is the P, and A is what? A is basically the states S. So A is S and P is equal to this. And if I run this, it gives me an error. P must be one dimensional, and P is what? How many dimensional? It's a 2D matrix, I guess. Yes, it's a matrix, right? So we need to index it to 0. Is it? If I index it to 0, does it help? No. Let's see. No. So let's write it as NP array. I hope that fixes the problem. Yes, it fixes the problem. Yes, now we can see from state C, we transition to C. Now, if I run it again, it's C again. If I run it again, C, 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 V, right? You see the transition to V, right? Again, C. If I run it again, it S. So if I just try to print all the transition, it will be like this. For transition in range 10, or let's say 20, we want 20 next transitions, print. This is the next state, right? So next state is equal to this. Now you see, we need to also, we cannot directly always transition from start state, right? So start state should be the next state would become the start state for the next transition. So we print the next transition and we change the start state to the next state. So for the next transition, the next state will become the start state for the transition. Okay. Okay. If I just run it and print all the transition, and let's say first print the start state, print start state, and this gives me the transition for that Markov model. We can actually do something like this. End is equal to comma, and so here end is equal to comma. Yes, so this is my transition, and if I run it again, it will be a different set of, like, I need to basically start from the same state again, otherwise it starts from the last one. If I run it, you see there are like different times the state transitions are actually different, but it comes from this transition, this kind of Markov process. Okay. If I run it again, you see, I can run it for longer also. So I can run it for 100 states, and it still gives me
more V's are there because 80% is there.
yes. So more V's are there because there is like 80%. Yes. Got it? So now this is our Markov process. Now let's design the Markov reward process. Okay. What we will do, we'll use the same code, same thing. Let's add some reward values to the chocolate and all those things. So let's go back to the disk and modify the diagram. Documents, nptel, rl. Yes, let's have a copy of this diagram. Rename it as Markov.
You are
Reward
modeling
process.
using random numbers, right?
Yes. So not random numbers. We are
Not random, no probability.
yes. So this is the probability dynamics we have. So assume that you know the world. Now how to model it in code. So this is how you can model it in code.
Somewhere
Okay.
one function you put a random, right?
Yes.
NP
So
dot random.
This is called choice. So basically you're sampling. Sampling is a random process, right?
Okay.
You're sampling from the probability transition array. You are like, let's print some other things, right? That would be very next transitions possible. Print.
So all these cannot be calculated manually, correct?
Yes, it has to be a random. Yes.
It's a
Print.
statistical process.
Yes. So print possible transitions. Transitions are zip list, zip state s comma p. Oh, sorry. Next PR. Let's see if that helps or not. Let's do. Yeah. Oh. Next PR. Yes. See, this is how things are going on actually. Let's name it 10. Yes. So you start from C. These are the possible transitions, and then again you start to C. Then basically transition to C. Then these are the possible. Then from C, these are the possible transition. So here the random process chose C. Sorry, S. So S is transition. Now S to C again. From S, these are the possible transition. So it chooses this transition and move back to C. Again it chooses to S, and then if I run it again, right? See, now transitions are entirely different. It chose to transition to V again. Got it? But these transitions are coming from this process. Okay. Okay. Now reward process. So for reward process, what we will do, we will basically have this thing. We'll only add numbers for the state. So let's say how much I like strawberry or how much I don't like strawberry. Based on that, I will add a number. If I just full screen it and zoom in, put in edit text. Let's say R is equal to, let's say I like chocolate a lot, right? R equal to 10. Increase the text size, make it bold. That's it. Okay. Now this is my reward for chocolate. If I copy this and paste it for vanilla, I don't like vanilla, so let's say this is my reward for vanilla, and if I paste here, and strawberry I like it so and so, like so it's like 5. Now this becomes a reward process. Okay, if I just save it and let's open it up again. Yes, the rewards are saved. Now we don't have to change it too much, our code, right? We just have to add the reward process aspect to it. So this Markov reward process. Now our process is what? No. Image insert C mrp.png and width to 500 pixel. Yes, this is my Markov reward process. And like one thing I can think of, a good example is, let's say when I was a kid, right? Then my mom used to buy me ice cream, right? And she used to buy it on her preference. Maybe I could not talk during that time, right? So that's the action is taken by my mother. I am just eating the thing. So even if my mom buys me strawberry most of the time, let's say, right, I am getting a reward of 5. But because I cannot express my action, right, I still have to follow through whatever the other person is taking in for me. So that's a basically you are not taking action into the system, but you are observing the reward or getting the rewards. So how to code it? Only thing that will be changed is, let's say, copy the state to array, fine, copy the probability transition. Okay. Now there will be another thing called reward. R is what? For S it is 10. For chocolate. C is 10. Let me charge my laptop. 1 minute. My laptop charge is almost over. Yes. So R for C it is 10, for V it is -1, and for R it is 5, right? So -1, 5. That's the reward matrix for us. Okay. Now transition, how I can take transition? Same, I need to have a state to classical like mapping. These are my state to classical mappings, and I need to have this transition code. This thing. Okay. Now only the thing that change is because the states have now rewards, right? Now we also, after we transitions to a state, we also print out the reward. Basically, whenever we are in a state, we will print out the reward. Okay, so this is the reward. So like let's write it as reward, RD, and to get the reward, we need to know the number of the state, right? Where we are. So it can be just a mapping, like it's just dictionary also. No need to be very formal with this. Later on, the states will be represented as numbers. So 0th state, 1 state, 2nd state, like this. S, T, and S. Okay. Now we'll also get the reward for the state. Sorry, reward for the state. Start state, and then for the next state, we'll wherever we are printing possible transitions at this next state, comma next state. Yes. So this is my, see, this is the thing. Yes, yes, I'll also send you the code files. No worries. Okay. Now this is my rewards. Now see, there are two new constructs that come into picture. One is so from here, what is happening? We can only see transitions. We cannot. Someone has a microphone on. Wait. Yes. Okay. So we cannot do anything with it. It's just transitions, purely transitions, right? But for here, we can see rewards also. So now that gives us two new things. We can just mark it in the here also. And let's put this image instead of that one. Yeah. Okay. Total reward. This is also there. Okay. So not only return is a theoretical concept, but total reward is basically the total, like if you transition for a long time, how much total reward you are getting. So I can just go ahead, go here, and because of the total reward, I can now have a total reward variable. Total reward is equal to what? Total reward can be 0 initially, and then as I transition, this is my next reward, basically next state, and next reward is at R, next reward. Wait, screen. I'll fix the screen issue later on. Wait, no worries. Maybe it's because I have not restarted. Reward is equal to this. Let's write it here. Next state equal to that. Now I can, after I see the next state, next reward, I can add it to the total rewards, right? Total reward plus equal to next reward. And after I transition to the entire system for 10 steps, I can print total reward observed is, sorry, total reward. Now if I run, see, I now can compute total reward. This is another new thing that I can, that comes with MRP. Again, if I run, it's 56. Again, if I run, it's 30. So if I run for a longer time, 100, it's 470. If I run it again, it's 430. You see, this is called total reward. Now return is a theoretical concept that we will learn, I guess, in the next class. So it's like almost we are at the 2-hour mark. So this is how total reward is computed. Now returns is actually a state specific thing. Okay. So would you fix up E? Must be one-dimensional array. Yes. Okay. So any doubts till now? So with Markov reward process, we just have a new thing called total reward. Now next class we'll discuss about return, which is a RL, like a very crucial concept for reinforcement learning. Later on, all the algorithms that you will see will have this concept of a return. Okay, and yeah, like next class we'll also code MDP. So how you can code an MDP. Okay, and then I'll introduce you to this library called Grid World. You can take it, can try it out in whenever you got time. And this, yes, and this library would help us to implement all the RL algorithms that are there in the codes. Okay, so be it, let's review the outline once again. This is the outline, right? So apart from bandits is a separate class of algorithm. This full RL, MDPs, Bellman optimality, all those things are based on this concept of MDP, MRP, and sorry, MP, MRP, and MDP. Okay, so till from here to here, all these things use this kind of information. So the assignment of week 1. See, I cannot. So the group, like, is week 1 evaluations are done. Week 1 evaluations are done or not?
Sir, no, sir. The evaluations are not done, sir. But
Yes.
this is a
So
clarification on the question itself, sir.
yes, but it's still on the submission phase, right?
Yes, sir. Well, if you know the question, I think my doubt will make sense because
Okay.
the options are little confusing for me. Maybe if you feel like that, I can ask you personally.
Yes. So like better to discuss the questions after the submission cycles are over. So from next class onwards, I will also discuss the previous year questions. Okay. Yes. After, yes, let's discuss after 5 August. Because if I discuss anything on the assignment question before the submission deadline, it will be unethical, actually. Okay.
Okay, sir.
So
This
anyway,
was a doubt on the
yes.
question itself, sir.
Yeah, anything related to the query. So if you have any doubts regarding whether the question is correct or not, you have to mention in that Google group that you have. So all the TAs that those set the question, right? We usually don't set the question. So PMRFs don't set the assignment questions. We basically practice the previous. We made you practice the previous year's questions and discuss any doubts after the submission cycle is over. So better to know your, better to ask your doubts in that Google group. They will give you a better solution.
Okay, sir. Thank you.
Okay. So anyway, we'll discuss the problem after the submission cycle is over. So if there is any like let's say the question is wrong or something, they will fix it. No worries.
Okay, sir.
Okay. Now this is the apart from bandits, all the other algorithms use this knowledge of MDP, MRP, and MP, right? So we'll continue from coding an MDP and learning more theoretical concepts like policy and all from the next class, and also practice the previous year questions. So that's important for the for scoring good marks. We need to also practice previous year questions. Okay, that we'll do from next class onwards. Okay, now this is the evaluation criteria. Just to touch it very briefly. So your assignment score will be 25% of the best 8. Okay, so there are total 12 assignments in the course. They will take best 8 assignments and it will be 25% of your total marks. Okay, and your last, like, there is a final exam which is of, I guess, 100 marks, and that will be part of the remaining 75% of evaluation, 75% of the score. Okay, and your final score will be basically the part from your assignment, 25%, and 75% from the exam. Okay, and also like the assignment questions can be of any type. So quizzes, programming tasks, essay submissions of anything. Okay, so it can be of different types. Okay, and you will be eligible for a certificate if you score more than 10 in the 25% of the assignments and more than 30 in the 75% of the final exam. Okay, if you made these two criteria, which at at bare minimum you need to score 40 out of total 100. Okay, so this is the requirement for get a certificate. Okay, so yeah, I guess after we revise the previous year questions and also do the um, do implement the theoretical aspects of the course, then I guess it will be very helpful for you to score higher than 40, obviously. Okay, so what we can do, I'll share the slides. Where I should share the slide? You already have the slides in the group in that chat, right? So there is the WhatsApp link there. Okay, so if you guys want to join that WhatsApp group, I'll also keep on sharing the materials over there. Okay? Anyway, it will be there in the common. There is a common sheet. Let me share it with you. Yes, this is the session. This is the public sheet. No, not this one. Session sheet.
There is a place for you to upload. And
Yes.
the
Oh, yes.
course.
So, do you have access to that sheet?
Yeah, I have the access.
Okay, okay. So I will upload there as well if you want to join in the WhatsApp group so that you guys can discuss among yourself. That's also okay.
Yes, yeah, there is a title named Problem Solving Session, July 2026.
Yes.
Something that header it is there. We go there, there is Excel sheet where you can provide links.
Yes, yes. So we'll provide the slides, the code we do in the class, and also the video link. Video will be uploaded to YouTube, and then that link will be shared.
So you will be the only person to giving tutorials on this, or
usually if the course is very large, so if large number of participants are there, then usually more than I guess there are two PMRFTs. Okay, but I need to
course
check.
there are two.
Yes, I think so. I think so. I'll confirm it. I need to open that new sheet. Wait, let me confirm it. Wait.
Yeah, previously when we attended some machine learning courses, so two people used to be there, and each will take independently.
Yes.
Some aspects and different aspects of the session.
I think this is not a huge, this is not a Python, it's like not 6,000 people. So Python has like 6,000, 7,000 people. Okay. So this one is a more specialized course. So I don't think there will be there is only one T, I guess me.
Okay, then yeah, we enjoy your lecture and thank you very much.
Yes. So give me feedback over the course so that I can basically tune my content based on your preference. Okay. So if you need more of a question answering sessions, then we can switch to question answering for some day, and then again switch to theoretical and practical implementation of the systems. Okay.
Sure, that will.
Okay. Okay. So
some problem solving session will be there now in every session.
Yes, because this is like an introductory class, so I need to first set up our kind of common grounds that this is the system we are trying to learn over the course. That's why I didn't took any question answering session today. But yeah, later on we'll also do question answering from the previous year questions.
Yeah, great. Okay. That would help. I think everything will help.
Yes.
Whatever.
Yes.
Conceptual.
Yes. Let's see. I hope we can have a great time over the entire course. Okay, I'm stop. Thank you. I'll stop recording the session. Yes, I